Hello and welcome everyone to the next event in our webinar series featuring our very own Dr. Gar-Wing Truong, Lead Scientist at Thorlabs Crystalline Solutions. Gar-Wing will be presenting a talk entitled 400,000 Finesse Mid-Infrared Mirrors for Cavity-Enhanced Sensing. My name is Garrett Cole, manager at Thorlabs Crystalline Solutions here in Santa Barbara, California. And as a colleague of Gar-Wing's since 2017, I take great pleasure in moderating today's webinar. For a quick bio, Dr. Truong is lead scientist again at Thorlabs Crystalline Solutions and earned his PhD in experimental physics from the University of Western Australia, working on precision spectroscopy of atomic vapors for primary thermometry. He was awarded a Fulbright postgraduate scholarship to perform research into cavity ringdown spectroscopy at NIST Gaithersburg and subsequently took a postdoctoral position at NIST Boulder. So he covered both NIST locations, which is quite exciting. Working on atmospheric dual chemistry trace gas detection. Dr. Truong then joined Crystalline Mirror Solutions, now Thorlabs Crystalline Solutions, bringing his expertise in the application of low-loss mirrors for time-frequency metrology and cavity-enhanced optical sensing. He remains active in the research community, contributing to high-impact peer-reviewed academic papers and generating patents, as well as by chairing and serving on various conference committees. Throughout Gar-Wing's talk, please feel free to submit any questions that you may have using the Q&A tool. Gar-Wing will then be answering these questions following his presentation. So at this time, I'd like to hand things over to Gar-Wing, and I look forward to his presentation.
All right, thank you very much, Garrett. It's great to be with you all. Thank you for joining the webinar. The title is a mouthful, but I will tease out each term and hope that I can give you a flavor of what we've been doing in our labs. So by the end of this talk, I hope that you will learn something about low-loss optical coatings, in particular our crystalline supermirrors, how we characterize these coatings, particularly because they are such low loss, and maybe inspire you to do some applications of your own after seeing how we have applied these mirrors to cavity ringdown spectroscopy. So let's jump right into it. And the first question we should ask, starting right at the beginning, is what is a mirror? So on the left here, you see a typical modern first surface mirror that you'll find in most labs. It consists of what is known as a substrate and a reflective coating. It's actually the coating itself that does all the work, does all the reflecting of the light, but because it's so thin and fragile, it can't really take shape on its own, and the substrate is the solid thing that you adhere the coating to in order to handle it and to keep its shape. We can have a whole webinar on the substrates alone, but suffice to say that often they are glass, and but they can be other materials, and you'll see that in the talk later on. We won't focus on the substrate today. We'll be looking at the reflective coating, and these can broadly be categorized into two types: metallic coatings and these interference multi-layer coatings. So metallic mirrors, you're probably all familiar. It's a deposited layer of often gold or silver, aluminum, tin, or nickel. They're very nice. They give you 95% reflectivity or more in the visible through to the mid-infrared. So very broadband, fairly easy to make, fairly cheap to make. However, the physics of the metal coating itself kind of limits you at that level of reflectivity. And if you needed more, you'll have to go to these dielectric or interference coatings. They're made up of alternating layers of high and low index materials, often silica and tantalum oxide. You'll see in our mirrors actually made up of gallium arsenide and aluminum gallium arsenide, but the principle is the same. So these can easily give you above 99% reflectivity in the visible and in the near infrared. And if you want the ultimate reflectivity, the state of the art would be to get something like 99.999% reflectivity. And often this will be at the cost of being much more narrow band, but you get this level of high reflectivity. And I will term such mirrors with such high reflectivities supermirrors. So with all this talk of reflectivity and the pursuit of ever increasing reflectivity, one can ask, well, what are the fundamental limits? So if you look at the schematic here, I've shown our coating or a coating disk, that's the gray disk on a glass substrate. If you have incident light, some of it will be transmitted, some of it will be reflected, some will be absorbed, and some will be scattered. And by the conservation of energy, the sum of all these loss channels, reflection, transmission, scatter, and absorption, must be unity. Transmission is something you can design for. Often with more layers, you'll get less transmission and more reflected. But that is a design parameter. You can choose what transmission you want. To a lesser degree, you can't really choose scatter and absorption other than to do your best, right? And these are parasitic losses. So absorption can come in the material. Scatter can come from, for instance, roughness in the material. So you're obviously trying to minimize these non-useful losses. So together, transmission, scatter, and absorption will limit what your reflectivity is. And to say it in a different way, that's the sort of boxed equation there. All I've done is rearrange the energy conservation equation above. And it's sometimes more convenient to talk about 1 minus R because rather than listing 5 nines, for instance, of reflectivity, 99.999%, you can just say 10 ppm as 1 minus R. And supermirror levels of performance are those sort of typical numbers you see there. And often you want to keep those parasitic losses at the sort of ppm level. And it turns out that in a lot of applications, the breakdown between 1 minus R and S plus A is important. And you want to keep the contribution of the parasitic losses to be a small fraction of 1 minus R. So then why pursue these high reflectivities at all? Here's a couple of examples, by no means exhaustive. But if you consider multipass gas cells that are often made with metallic mirrors, you have an analyte that's not very highly absorbing, and so you just want a very long interaction path. And so these multipass cells give you a highly folded optical path, sometimes with hundreds of bounces and up to hundreds of meters of interaction length. But if you think about it, for 100 bounces with reflectivity of 99%, the transmission through this cell after all those bounces is only 37%. And obviously, if you have lower reflectivity, this is a strong function of reflectivity. And so that cell transmission is going to drop rapidly as a function of reflectivity. And then if you take it to the extreme, and rather than have sort of a highly folded optical path, if you take it to the limit and just fold that path back onto itself, you have a resonant cavity, a Fabry-Perot cavity. And in this case, with very high reflectivity dielectric mirrors, you can achieve tens of kilometers of optical path in sub-meter long cells. And when you're on resonance of these Fabry-Perot cavities, you can get typically with good mode matching and good losses up to 80% or more transmitted when you're on resonance. And again, that maximum transmission is going to be dependent on the breakdown of your transmission versus your parasitic losses. So why do we care about sort of making these cavities? Well, it turns out it's a very nice way to do trace gas detection. You're trying to detect very small amounts of absorption, which ordinarily you would do as a radiometric measurement. So you're just trying to detect a small absence of light from the input beam. And that's actually a very difficult measurement to make. So this cavity ringdown approach allows you to convert a radiometric measurement to a time measurement, and you can measure time with great precision, and that actually gives you a lot of its sensitivity. And couple that with the path enhancement, you have a very sensitive trace gas detector. So if you couple in some light into a Fabry-Perot cavity, that light will bounce around in the intracavity space, and each time it hits an end mirror, a little bit will leak out. Now, that leak rate is going to depend on the losses of the mirrors. So the lower the losses of those mirrors, the longer the light is trapped inside, and the decay of that light outside the cavity is going to have a longer time constant. And so that drives the motivation for very low loss mirrors. And then once you introduce an analyte or an absorbing species into the space between the mirrors, you'll introduce a little extra loss. And so then when you're sampling both the loss of the mirrors and the analyte, that time constant of the cavity drops a little more, and it's exactly the comparison of the empty cavity time constant to the loaded time constant that you're using to detect the presence and the abundance of the absorbing species. So as we talk about cavities, Fabry-Perot cavities, I'm going to use this figure of merit known as Finesse, and it's nothing more than this nonlinear combination of reflectivity. It's just an easier way to quantify cavity performance when you're up at these many nines of performance. And to orient you, if we have the scanning Fabry-Perot interferometers, the SA30-144, it's a visible to near IR interferometer. That has mirrors with reflectivity of 99.79%, and that's a finesse of 1500. 99.90% reflectivity gives you a finesse of about 3000, and that's like a laser line mirror. And moving on to supermirror levels of performance, 99.997, for instance, our XM11R8, that gives you a finesse of 100,000. You can, even in our catalog, you can get these XM14R8s for 1550 use, and they're 99.999% reflective, and that gives you a finesse of 300,000. So really what I'm trying to drive home here is sort of supermirror levels of performance are on the order of 5 nines of reflectivity and on the order of 100,000 or more in this metric known as finesse. So then how do we make these crystalline supermirrors? I've talked a lot about them. They are just a different way of making a very high reflectivity coating. We start with gallium arsenide and aluminum gallium arsenide multi-layers that are grown by MBE. It's a semiconductor technology. We grow them on a native substrate, and then we define, lithographically define a die that we can separate just the multi-layer from the original growth substrate, and then we directly bond it onto arbitrary optical substrates. So, for instance, glass. And the nice thing here is we can leverage the best tools to make the coatings, and then bond these coatings onto the best optical substrates for the application in mind. And we can obviously bond to curved substrates in order to make stable resonant cavities, and we cover wide ranges of wavelengths and geometries, and all of that is customizable. So here's an example of a near-infrared supermirror, crystalline supermirror cavity that we've made in the past. You'll see, again, there's that 1-inch glass substrate with the dark coating disc in the middle. There are actually 2 of those mirrors that are contacted onto that sort of triangular looking piece of glass that's known as a spacer. It simply holds the 2 mirrors at a very fixed distance apart. And here we see that the finesse we achieved was above 700,000, and that corresponds to a 1 minus R of about 4.4 ppm. There's a small typo here. The mirror transmission was 2.5 ppm, and the excess losses was 1.8 ppm. So that's sort of what we have been able to achieve, the very highest finesses that we've been able to achieve. So why make these interferometers at all? Well, it turns out that these high finesse cavities are at the heart of atomic clocks. High finesse cavities are also found in quantum limited optical interferometry, so benchtop sort of science, fundamental science experiments. And we hope to see them in the next generation of gravitational wave detectors as well, because they are also fundamentally Fabry-Pérot cavities. But today we'll talk about the use of these mirrors in cavity-enhanced sensing. And that's the bottom left box there. And in particular, we want to talk about spectroscopy in the mid-infrared. For those who know, there are some good reasons to go to the mid-infrared. There are a lot of species, molecular species, that are important in a variety of fields that are listed here that have stronger absorptions where you can address the fundamental vibrational transition modes of these molecules in the mid-infrared, and at even longer wavelengths, the so-called fingerprint region is useful to access, as the spectra for these complex molecules are more sort of orthogonal to each other and easier to interpret. So our gallium arsenide platform is well suited to moving to the infrared. What I plotted here is the absorption as a function of wavelength. You'll see that it's very difficult for us to go to the visible, but we can maintain low levels of absorption well below sort of tens of ppm out to nearly 10 micron center wavelength. And the key here is just in the material growth to keep the background doping levels during the MBE growth very low, and that's how we maintain these low absorption values. So then how do we actually grow and make these crystalline mid-infrared mirrors? Well, the naive approach would simply be to grow the entire stack that we need in a single MBE growth and transfer them onto an optical substrate, kind of the way I schematically talked about a couple of slides ago. The thinnest multi-layer that you can achieve is a quarter wave stack. But of course, at these long wavelengths, the quarter wave itself, it turns out that the total thickness that you require due to the longer wavelength, as well as the number of layers that you need in order to achieve low transmission, really pushes the limit of that growth technique, and it becomes an unstable growth, and you can't reliably get multi-layers that way. So we have this cute trick where rather than grow the entire design stack in a single MBE growth, you actually just grow half of it, exactly half of the design. And schematically, you can think about taking a single wafer, which could be 6 inches. It's much larger than the coating size that we need. You can take that much larger wafer, fold it on itself, and making it double thick, and actually achieve your design sort of number of layers by doubling up on the wafer. And so that's shown schematically here with 2 DBR half mirrors that are bonded to themselves, and that whole assembly then bonded onto the optical substrate. So that's a pretty sort of, harebrained idea. And so our very first go at it, we were conservative. We designed for a nominal transmission of 140 ppm, so certainly by no means supermirror levels of performance, but we wanted to start somewhere, right? And be able to check out this technique. And it turns out that it worked very well. At the design transmission of 140 ppm, that actually gives you a cavity finesse of 20,000, and that is solely limited by our design choice of such a sort of high transmission. And that gave us hope that we can do well with these types of coatings. But the downside is we have this 2-step bonding process, which actually made scaling these mirrors to production a little difficult. So then the next thing we kind of recognized was that, well, actually it's only the first few layers of the interference coating that sees the majority of the electric field. So what I've shown here is the index as a function of distance into the multi-layer. So you can see there's high index, low index, high index, etc. And it's exactly a quarter wave stack. Coming in from the left is some incident light, and then the blue squiggle is the expected field inside the multi-layer. And so you can see it decays quite rapidly. That field decays quite rapidly, and most of the absorption is dictated by where the field is high. So what we can actually do is just make sure we use good materials for these first few layers. And although we do need many other backing layers to get the right transmission, the layers towards the end where the field is tailed off is not so important. And so this gives rise to what we call a hybrid coating, where you get the best of both worlds. You start with the optical substrate, you put down a conventionally coated half mirror, and that may use materials that are slightly more absorbing than our crystalline materials, but again, that's where the field is lowest. And then we sort of overcoat this with our crystalline half mirror on top. So this has been a very successful approach. You see that we've characterized these hybrid mirrors, and at the center of the stop band, in this case, it's about 4.45 micron. The finesse is well above 400,000, right? The total losses there are about 7 ppm with a very favorable breakdown of transmission of about 5 ppm to about 2.5 ppm of parasitic losses. So to give you some context, the highest finesse mid-IR mirrors at this sort of wavelength we've found in the literature is about 60,000. So we're doing fairly well in comparison to the literature. And to demonstrate some application, and this will be the last point of the talk here, you can see there's a star just past 4.5 microns. It turns out there's some nice absorption lines we can look at there. And we teamed up with some folks at NIST, some seasoned spectroscopists there. They were interested at looking at process gases and high purity nitrogen. And in this supposedly pure nitrogen sample, they were able to see 37 ppb of CO. And if you look at that trace on the left, you'll see that the CO line doesn't fully explain the measured dots, and there's a little shoulder and deviation from the red predicted trace for CO just to the right there. And that's actually attributable to 140 ppt of N2O. And indeed, if they moved the spectrometer to a wavelength where N2O has an isolated line, they were able to confirm that, yes, there was 140 ppt of N2O. And to give you some idea, the natural abundance of N2O is 320 ppb. So that's pretty impressive in my books. Shows you sort of how sensitive this technique can be. And with a little averaging down to a few seconds, we see a minimum absorption coefficient of 2.5 by 10 to minus 11 per centimeter. And for a linear ringdown, linear spectroscopy or linear interaction with gases in a cavity ringdown setup, that is the lowest absorption coefficient that has been reported. And that was enabled solely by the lower loss mirrors at this wavelength. We can talk more details about the spectrometer, but it fundamentally is Fab-Pro cavity. It's 75 centimeters long, and this really opens up the possibility of doing some exciting science that otherwise would have to be done at, say, accelerators. That would be like a facility-sized spectrometer. Oops. All right, and so I'm excited for these results, and even more excited that these mirrors will be coming to the catalog. You can see the preliminary specifications here. They'll be at center wavelength of 4.5 microns at room temperature with a reflectivity of about 1 minus R, about 15 ppm. Typically, they will be high reflectivity than spec, but we've been a little conservative here. They'll come out on 1-inch substrates as sort of shown. You can get them with 1 meter radius curvature or planar, schematically, sort of the background there is to show, we have a substrate that we first coat with an amorphous or conventionally coated backing layers that we then overcoat with the crystalline material. So with that, I'll conclude. I hope that you've learnt a little about the history of crystalline mirrors and their excellent optical and mechanical properties in the near IR, and how we extended this technique to the mid-infrared, and how our mid-infrared coatings now routinely show excess losses well below 10 ppm, and that enabled us to make cavities with finesse of above 400,000. Thank you for your attention. I hope this has inspired you to explore this exciting wavelength range, and I'm excited to see these mirrors come to the catalog really soon. Thank you.
All right, fantastic. Thank you very much, Gar-Wing, for that excellent and very informative presentation. I'd like to remind everyone that the Q&A session is still open, so feel free to continue submitting questions that you might have. I'm going to start with a quick one, Gar-Wing. Any guidance on, I know you showed some results at 1550, and here we're discussing 4.5 microns. What sort of wavelength ranges could be covered in the interim for custom optics?
Yeah, for sure. So good question. So really, we can cover sort of wavelengths. We're confident we can cover wavelengths in between 1.5 through to 4.5 microns, and that's sort of given the known absorption curve here. And of course, depending on needs and depending on sort of how much more absorption you could tolerate, potentially we'd like to go out to even 10.6 microns, and there's obvious applications out there.
Yeah, thank you. We have a question here about the manufacturing process. So does the bonding require an epoxy or some other adhesive, or can you describe just generally how that works?
Yeah, sure. So there are definitely no adhesives, no epoxies. For those who are familiar with optical contacting of bulk optics, where if you have sufficiently smooth surfaces and you bring them in contact, they will spontaneously stick. It is the same principle here, and it's a principle that's actually well known to the semiconductor industry as well. So the key ingredients here is to have clean, smooth surfaces, and these will spontaneously stick with no adhesives and no interlayers.
Yeah, no, very nice. And there's a question about the cavity configuration also. I think there was a bit of a misunderstanding that the cavities are sealed. And so there was a question about how you would get your sample into it. And then I'll follow up one more level deeper was, what sort of pressures would you expect within the cavity volume? Atmosphere, millitorr. I'll let you take over.
Yeah, sure. So yeah, actually, sort of shown schematically here, it's actually pretty close to real life. So you kind of just hold two mirrors, and the intracavity space is open to flow of analyte or sort of your sample of interest. Really, it's just a matter of holding these mirrors in a way that just allows you to adjust them into parallel and get resonance. So if I come to this photo of the NIST spectrometer, what you're looking at are sort of two specially designed vacuum end flanges that hold the mirrors, but then the intracavity space, you may not quite be able to tell, but there is a gas inlet and also a gas outlet because they're interested in doing a flow. But that's how you would introduce your analyte into the cavity. The cavity is sealed from the atmosphere, but the intracavity space is not sealed from the analyte. I hope that answers the question.
Nice. Yeah, that was very nice. Going on to an additional question. Can you make any comments on the bandwidth of the mirrors? So you talked a lot about the maximum achievable reflectivity, but what sort of spectral bandwidth would these have?
Yeah. So that very much depends on how you want to define that bandwidth, and that would depend on your application, right? So I think the best way to answer that question is to look at this plot here. So for instance, at the very center of the stop band, it's 7 ppm of total losses. But if you wanted to call, the bandwidth, the points at which you start to hit, say, 10 ppm of total loss, well, then there's, just over 100 nanometer. But if you're able to tolerate up to, say, 100 ppm of total loss, then obviously that bandwidth goes up. So I think it's really this plot that answers the question.
Yeah, no, thank you very much. Yeah, we have questions flooding in, so give me a second just to sift through these. Yeah. Yeah, I think, let me get to here. So is there requirements on surface roughness, both on the surface of the mirror or with the substrates that you can comment on?
Yeah, for sure. Typically we want angstrom levels of sub-angstrom levels, I guess, of roughness for the substrates, and similarly for the coatings, but obviously we control the coatings. So if you were thinking, if this question is towards sort of what sort of substrates we could use, and whether or not you can supply your own, you can certainly do that, and that's sort of the ballpark levels of smoothness that's required for this process.
Yeah, very nice, thank you. Since we're pushing over time, I'm going to do just one more. I'm going to end with a forward-looking question. Do you see a path to move to longer wavelengths beyond 4.5 microns with this technology?
Yeah, good question. So again, it's sort of application dependent somewhat. For those who cannot tolerate more than a ppm of loss, then you're sort of limited down here. And if, sort of sliding scale, you can do tens of ppm losses, then clearly we can continue to push out. And we'll, want to do that, and we'll fill out this curve, this theory curve, we'll pin a little better with more measurements. But again, our goal right now is to march out towards 10.6 micron.
Yeah, very nice. Well, again, I would like to thank the audience for attending. I'd like to thank Gar-Wing for that very fantastic presentation. Clap locally here. I will note that on October 23rd, so 3 weeks from today, we'll have a webinar focused on ultrafast technologies with Professor Oscar Martinez from the University of Buenos Aires presenting. And that'll be titled Exawatt Lasers to Nonlinear Microscopy, Taming Ultra-Short Pulse Shapes. So be sure to register for that event at thorlabs.com/webinars. And again, thank you very much for attending, and we hope to see you again soon.